Welcome to this Winemakers Research Exchange virtual sensory session. Today, we will be discussing experiments centered around sulfur dioxide, including looking at sulfiting agents, as well as some alternatives to using sulfur dioxide. My name is Joy Ting, and I'm the research enologist for the Winemakers Research Exchange, and I will be joined today by three different experimenting winemakers, Matthieu Finot, AJ Greely, and Kirsty Harmon. Before we start, I did want to remind everyone that in addition to providing you an experience of tasting these wines and discussing these wines, this is also our opportunity to gather blind sensory data from you about these experiments. So if you received wines in the mail and you have not yet filled out your sensory sheet, I'm going to ask you to actually sign off of the call, go ahead and do the sensory analysis, and then sign back onto the call. And if you miss a little bit of the discussion along the way, we are recording this session, and so you can watch whichever portion you've missed along the way. So with that, we'll go ahead and get started. Before we start talking about the experiments today, I did want to give just a very brief kind of Cliff Notes version of some things to keep in mind when we think about sulfur dioxide, and then we'll pull concepts from that throughout our discussion today. So when we think about sulfur dioxide, When we think about sulfur dioxide, this is probably one of the most common things used in the winery as an additive for all kinds of different reasons, but primarily because it has antimicrobial and antioxidant properties. We already have a number of resources on the Winemakers Research Exchange website to help you to understand various things about sulfur dioxide if you're looking for kind of a refresher course and some of the chemistry behind this. So in the Learn section of the website, we have two different kind of modules there. And these are sort of the things that we'll send out as part of our newsletters, kind of review articles on background information. So we've got one on SO2 management. That includes some of the basic chemistry of SO2, as well as some ways to think about what targets you might be trying to aim at, and a few things about ways to reduce sulfur dioxide use. We also have a Learn module on SO2 measurement methods. So again, this is probably one of the things that is most likely to be measured in-house in our wineries. There's many different methodologies to do that. So we've got an article there on the pros and cons of those different approaches. And then we also have a number of different reports of experiments along the way. So the library section of the WRE website contains all of the reports, the finished reports from all of the experiments we've done in the past. We have so many on sulfur dioxide, it sort of has its own section of the library. So in the library, we've got everything arranged by kind of where it happens in the course of the wine, the life of the wine. This would be the SO2 articles are all found in the post-fermentation section under additives. And again, there's a number of different experiments that have already been done looking at how much to add as that original dose, the timing of those additions, and some kind of consumer reports types of things looking at different ways of measuring SO2, what kind of precision and accuracy you might find in that. So all of those resources are there for you. If you ever have trouble finding anything on the website, please just let me know and I'm happy to send those to you. But in order to facilitate our discussion today, like I said, I'll give you the quick Cliff's Notes version of some things to think about with sulfur dioxide. So regardless of what sulfiting agent you're using to add sulfur dioxide to your wine, as soon as that SO2 agent lands in either your juice or your wine, it interacts with water quite quickly. And it takes on one of three forms as it interacts with that water. So the first form is what we would call molecular sulfur dioxide. That's the one on the very left-hand side here. And that's one that's uncharged. And it really is kind of what it looks like when it's not interacting with any of the hydrogen ions or OH ions in the water. But of course, it doesn't stay that way most of the time. So most of the time, it's actually going to pick up an OH ion from the water to form what we call bisulfite. Bisulfite is a charged molecule. You can see it has one negative charge on it, and it turns out that's kind of important for how it works. And then we also do have a third form, the sulfite bianion, meaning it has two negative charges to it. But it's really those first two forms that we care about the most. So when we look at Which form our our sulfites are taking in solution, it really depends on our pH, and we probably have more than one kind at a time. So when we look at what's happening at predominantly a wine pH, most of our sulfur dioxide, most of our free sulfur dioxide is found in that bisulfite form. We have a little bit that's found in the molecular form. And as you can see, the more acidic the wine gets, or the lower the pH gets, the more we get into that molecular form. But within the pHs of wine, we're really dealing mostly with that bisulfite. The reason we care about that is that when we think about what our SO2 is doing, being antimicrobial and antioxidant, the different forms have different roles. So that molecular sulfur dioxide, that's the one that does most of our antimicrobial role. And a good way to remember that is that basically, in order to be antimicrobial, this thing has to get into the cells of the microbes. And the only way to do that, the only way to kind of get through the membrane system of the microbes, is to be uncharged. And so our molecular sulfur dioxide is the only one that's uncharged that can kind of sneak in and get into the cells themselves. Once it's there, it wreaks havoc on all of their metabolic systems and on their cell membranes and on their structural proteins and all kinds of other things. It's also that molecular form that is mostly responsible for sort of our volatile SO2 effect. So like when you sniff a wine and you can actually smell the SO2, that's mostly that molecular form, because it's the one that kind of goes back up into the air around it. That form can also be lost through aging if we have untopped tanks, as much as it can sort of volatilize off of the wine to sort of, for us to be able to smell it. It also can volatilize into the headspace and therefore be lost from our wine and no longer be having an antimicrobial effect. That bisulfite form is, though it is not, most of it is not antimicrobial, it still is very important in that it has an important antioxidant effect. And in this case, it's sort of antioxidant in a couple of different ways. One of those ways is that browning in wine is predominantly because oxygen has bound to phenolics and caused them to turn brown. In our white wines, we don't think about the phenolics very much, but we still do have plenty of phenolics in there, especially white wines that see skin contact. And so when they come into contact with oxygen, they can turn brown. Our bisulfite form of sulfur dioxide can bind to those phenolics and keep them from turning brown, and therefore prevent oxidation in that way. It's also important in other antioxidant functions, though, because it inactivates some of the enzymes that speed up the oxidation reactions. And so it's not only just keeping it from browning, but it's actually keeping some of those oxidizing reactions from happening. Unfortunately, it doesn't just bind to those things. It also binds to a whole bunch of other stuff that's found in the wine. So if there's and that's sort of what makes up that bound fraction. So when you do your SO2 addition, let's say you do a 20-part addition and you only get a change in your free sulfur of, let's say, 7 parts, where did the rest of it go? Well, most of it got bound to other things that are in the matrix of that wine. So a lot of the things there are the most important things, I guess, to remember there would be if there is sugar, if there's residual sugar in the wine, you should expect to see more of the binding happening there. And so you'll get sort of less efficacy in terms of your free sulfur. Acetaldehyde is, it's produced by yeast during fermentation. So when you kind of finish a fermentation and it has kind of that bruised appley kind of affect, that's acetaldehyde. Acetaldehyde can also be produced when ethanol comes in contact with air over time. It can become acetaldehyde as well. That's a very strong binder for bisulfite. Anthocyanins are also a binder for bisulfite, and so it's thought that a lot of our sulfur in our red wines are actually found bound to our anthocyanins. Now, I said that this doesn't really have much of a microbial effect, with one exception, and it turns out this exception is important for our discussion today. So the one antimicrobial effect that you can get from the bisulfite form is that it's thought to have some inhibition of malolactic fermentation. And the mechanism of that is kind of important in that what they think is happening there is that malolactic bacteria will consume acetaldehyde. And remember, acetaldehyde is binding to our bisulfite. So as the malic acid bacteria consume the acetaldehyde, that bisulfite gets sort of released and it goes back into solution. Depending on how much free sulfur you have around, some of that bisulfite might sort of equilibrate and take on take on that molecular form and therefore become somewhat antimicrobial. So depending on the circumstances, our bisulfite might have some effectiveness on antimicrobial forms because it's found so predominantly in that bound form. So I've talked a bunch about kind of binding and not binding. So another thing we do need to keep in mind, and it becomes important today, is thinking about the difference between total sulfur dioxide and what that means for our free and bound fraction. So when you add your sulfur dioxide to the wine, again, some of that is going to bind to your sugars or acetaldehyde or your phenolic compounds, and they become the bound fraction. And it's really only the unbound fraction or the free fraction that has most of those roles of being antimicrobial or antioxidant. But the total sulfur does turn out to be important sometimes, and we'll see that as we go through today. So I think we talked about that. So because the sulfur does bind, though, that means that when you do a sulfur addition, not all of it is going to stay as free sulfur. So oftentimes between 1/3 and 1/2 of that might end up as free, but the rest of it will probably be in the bound fraction. The proportion there really depends on the wine itself, where it is in the lifespan of the wine and the type of the wine. So the more things you have that will bind the free sulfur, the lower your proportion of free sulfur is going to be at the end. But also if you're early in the life of the wine, many of those things that will bind have not already been bound. So when you do your addition, more of it's going to bind up. As you sort of bind up those sites later in the life of the wine, if you say are carrying maybe a free sulfur of 25 on a pretty regular basis, then your additions probably won't bind quite so much. If it's really important to know exactly how much free sulfur you have, like if you need to get to a particular target, usually takes about 3 to 5 days for that binding to occur. So it's good to retest it after about 5 days just to see if you've hit your target. And then we should always expect that there's going to be some loss over time. We're not going to keep all of our free sulfur over time because of various different processes that are happening in the wine. And so we should expect maybe about 5 parts per million or milligrams per liter loss per month if everything else is good. So if everything is topped and there's no headspace and you're not introducing oxygen with any kind of racking or filtration or anything like that. As soon as you start interacting or introducing more oxygen along the way, you'll have faster losses as well. And then the last thing I'll say in terms of kind of our Cliff Notes version of SO2 management is just, most of the time we're managing it based on a particular target. So we're trying to get to a certain free sulfur target. And the decision of what target to aim at, I think, is really one that is sometimes hard to know what you're looking for. So if you want to be maintaining sulfur dioxide for antimicrobial purposes, then of course you're looking at the molecular sulfur. And we can see some of the targets here over on the right. The WRE website has a more complete list of kind of what different targets I found in the literature when I did a search of this. But whenever we're thinking about antimicrobial targets, we also have to realize that microbes are pretty diverse. And so different microbes are going to respond differently. So pH itself does shift how much of our free sulfur is in the molecular form, but it's also just overall kind of the low pH in the wine is overall just stressful to the microbes. And so you might be able to maintain a lower molecular sulfur if you're at a lower pH because stress is cumulative for those microbes. If you're at a high pH, you may need a higher molecular sulfur in order to stay in that antimicrobial space. Again, species of microbes are diverse. We could probably put strains of microbes in there as well. So as many strains of yeast as we have, we probably also have that many strains of Brettanomyces or that many strains of acetic acid bacteria. So they most likely will have different nuances of how tolerant they are to our sulfur dioxide. And then the stage of development of those microbes, if they're in an actively dividing stage versus if they are in just a metabolic stage, just doing their work, they have different susceptibility. Now, if you kind of feel like, I can't get to the antimicrobial target I want to get to anyways, I'm just going to do it for antioxidant purposes. First, I would say that if you are managing for antimicrobial, you probably have already met your antioxidant targets. But if you're not going to do that, the literature at least will say that about more than about 10 milligrams per liter or parts per million of free sulfur for red wines is a good idea for your antioxidant targets. For white wines, you need a little bit more. That goes up to about 20 milligrams per liter, mostly because you don't have other antioxidants hanging out in the wine. So in red wines, we have tannins, which are also antioxidant. In white wines, we don't have that. So we need some additional coverage. So that's kind of a quick little, run through some things to keep in mind for SO2. And like I said, we're going to kind of pull from that as we talk through today and sort of figure out what that means in practical matters. But we're actually going to start with an experiment today that was meant to kind of limit our SO2. And that was an experiment that was done by Matthieu Finot at King Family Vineyards. So if we can get Matthieu here, let's see. So Matthieu, the experiment that we're talking about today, you're muted at the moment. So maybe we can, there you go. Hello, how are you? Welcome. So we're really talking about an experiment that's sort of part 3 in a series for you, looking at your sparkling wine base. But your sparkling wine base is kind of inherently a low sulfur wine. So do you want to talk just a little bit about what your SO2 targets are for when you're trying to manage your sparkling wine base? What do you think about with sulfur? What are you even trying to achieve there?
Well, there's 2 things that I'm trying to achieve. The first one, I feel for the sparkling wine, we're going to do a second fermentation. So I don't want to start with my sulfur being too high. And also we work with wine that's got a fairly low pH, 3.2. And so I feel like the sulfur that I will be adding will be very, very active anyway. So I will have more molecular sulfur because of the pH. And because I'm going to need to do the second fermentation, I never want to have too much sulfur added to it. I'm trying to bottle my wine with less than 10 ppm of free sulfur. And so in the past, I've been really reducing the amount of sulfur that I'm adding to the wine post-alcoholic fermentation. Usually I'm adding 2 grams per 100 liters, so it's 20 ppm. After post-fermentation. Some of the issues that I had lately, it wasn't enough to prevent the malolactic fermentation to start after a while. Also, I do a barrel fermentation, so I've got constant oxygen going into the wine, and that's in fact make my free sulfur go down very, very quickly. If I was probably working in stainless steel, that would be probably easier to keep this 20 ppm and not have the malolactic fermentation. But in barrels, it becomes a challenge. So yeah, that's my goal, or that's my problem. I'm not sure.
Yeah. Well, that's the set of circumstances that you have to think about, right? So I think that does a great job of kind of setting up the experiments that we'll look at today. So this is actually kind of the third in a series of experiments. And again, you can see the reports for the previous experiments on the website. But I am going to kind of give just a little bit of background so that everyone kind of knows what we know so far on this question. So in 2020, Matthieu actually did some experiments where he wanted to allow malolactic fermentation in the sparkling wine base. And then in 2021, we'll look at the result of that in just a minute. But in 2021, he started to want to really prevent malolactic fermentation in the sparkling base. And again, as he said, a little bit tricky. Go ahead.
Because after tasting the comparison with the one with the malolactic versus the one with no malolactic fermentation, I prefer the one with no malolactic fermentation. So then after that, I was trying to prevent it. So yes.
Right. So that's a good segue here. So when we did that first set of experiments, there was a set of chemistry that year that Matthieu was like, maybe I need to let this go through malo because the chemistry was just really not lining up. And so what we did is he had 2 different batches of sparkling base, and for each one of them, he took half of the barrels and treated them with SO2 and ketosan, and half of the barrels he didn't do that, and he was going to allow malolactic to occur. And what we ended up finding at the end of that experiment was that the malolactic fermentation itself kind of led to things that we would expect to happen: higher pH, lower TAs, higher volatile acidity. And then we did have significant differences in the sensory, and it's sort of, there's a lot of malic acid to deplete in sparkling wine base. So like that much malolactic really brought on a lot of sort of butter, creamy, soft mouthfeel that ultimately wasn't really what Matthieu was looking for in terms of his winemaking goal for his sparkling wine base. But the other thing that we saw when we started to look carefully at those barrels is that it wasn't necessarily the 4 barrels that we stopped that we sulfured and gave Kitasan that didn't go through mallow, and it's not the ones that we didn't do that to that did go through mallow. What we actually found was 7 out of 8 of those barrels eventually went through some form of malolactic fermentation. And in the other experiment, we saw something like 5 out of the 8, and it really had nothing to do with that sulfur and that Kitasan. So that really led to this question of, you know, if this is not a flavor profile that Matthieu wants in his sparkling wine base, but his current protocols are leading to this set of circumstances where he's getting that to happen, what can we do to stop it while still maintaining those other things that he likes about how he's doing the fermentation? So it's in barrels, it's aged on lees, it's aged with low sulfur, all of that's for a reason, but it kind of sets up the situation where mallow is going to just be more permitted. So last year, and I guess the last caveat here, and I put this here on purpose, is to say, even if you're not making sparkling wine base, if you're trying to make white wines with low sulfur and you age them on lees, these principles still apply, whether it's for sparkling wine base or just kind of managing for low sulfur. So in 2021, we did a set of experiments, again, to just try to prevent malolactic fermentation. It was the normal sparkling wine protocol, except we had 3 treatments. One just got that regular, 22 parts per million of sulfur at the end of fermentation. One of them we actually treated with a Kitasan product, which is Stab Micro M, at the beginning of fermentation. That was at the manufacturer's recommendation to say, well, if you treat it early, then you might keep the culture from building up so that you won't have as much malolactic fermentation on the other side. And then we also had one where we treated with Kitasan at the end of fermentation just to try to prevent malolactic from happening in the barrels. Unfortunately, none of those was consistent in preventing malolactic fermentation. So anytime you see any of these lines kind of go down, that's plotting the malic acid. So in each of the treatments, we had at least one of the multiple barrels that we look at kick off and or finish malolactic fermentation. So this basically told us that this is a problem that, that small amount of free sulfur isn't probably going to help. And treating it with Kitasan does not seem to be consistent along the way. So we went back to the literature and we were like, what are the things in the literature that kind of say, how do you prevent malolactic fermentation from happening? And it turns out most of these were either things that Matthieu was already doing or things that kind of don't fit the winemaking goal. So the things found in blue here are things Matthieu was already doing. He's already aging these relatively cold. He already has a pretty low pH. These are all whole cluster pressed because they're sparkling, so there's not any maceration time there. And again, we tried with Kitasan and we didn't see consistency in that particular object. The other one here that we could play with was sort of getting things off the lees to sort of remove that microbial contaminant. But in Matthieu's sparkling wine base, those lees have a purpose and he wants to age on those lees. So we don't want to remove those. So this year we did choose a couple of other options for experimentation. One of them was looking at higher total SO2. So, one of the things in the literature is to keep the total SO2 above 50. Now, again, he didn't want to have that in his free sulfur because that might inhibit the sparkling fermentation. So we decided to try to add a little bit more sulfur at the beginning at crush, really with the idea of increasing that total sulfur. And the idea behind that goes back to that principle that when our acetaldehyde is consumed by malic acid bacteria, they essentially poison themselves with the sulfur that they release. There was a little bit of an understanding that this might be part of a reasonable protocol. When Eno France came a couple of years ago and did their sparkling wine seminars, their kind of standard protocol for sparkling did include adding 50 parts of sulfur at crush. And so we thought maybe that's just one of those protocol things that's baked in there that we don't think very, very often about kind of what's going on, but maybe that's why that's there. And then we had two other things that we wanted to try. One was the addition of fumaric acid, and the other was the addition of Hideki tannin. Now, these are a little bit, well, we'll see in just a minute. They're maybe less familiar as additives. So I did want to tell you just a little bit about each one of those. So fumaric acid is, I call it an old and new approach. It's one of these things that there were a couple of researchers on webinars last year that started talking about fumaric acid. But as I started looking into the literature, it turns out it's been around in the US for a long time. It was approved as an additive in the US in 1963. And there's a series of papers that came out of Davis in like the 1970s looking at this. It was only recently approved for use in Europe, and that was in 2021. And there's sort of this renewed interest in it because in some ways it might be a potential thing to think about with low sulfur wines and also with climate change concerns. Because basically, it's being added in order to prevent malolactic fermentation, but it is itself an acid. So, and it's thought to be, at least once, if you add it after fermentation, to be a relatively stable acid. So it sort of has this potential side benefit of acidulation. So when we look at sort of wines affected by climate change, they might have higher pHs. So that added acidity there might be a benefit in addition to kind of keeping your malic acid. I will say in the literature, there's reports of having some shift in the pH, but that does seem to be very dependent on the wine matrix. So we'll keep an eye on that in Matthieu's wines as we look at those data. It is technically probably a natural component to wine because it's one of the intermediates that's found in a very common metabolic process in the Krebs cycle. But I put quotes around that because it's usually not found in nearly the quantities that we would be adding it as an additive to prevent malolactic fermentation. So it's probably there in very trace amounts. What we're using it as an additive is in much higher amounts. But it does inhibit, it has been shown to inhibit malolactic fermentation, both before it starts. So if you treat it with fumaric acid before it starts, it does seem to inhibit. And then also under most circumstances, if malic's sort of underway, it seems to be good at stopping it where it is and not letting it progress any further. It is important if you're thinking about using fumaric acid to use it after the fermentation is complete. Yeast have an enzyme that will convert fumaric acid to malic acid. And then basically you've just increased your malic acid, your malolactic bacteria will go through and ferment that. So the recommendations are to add this after all of your yeast are kind of finished working. It does seem to be more effective at lower pHs. So that might just be because the acid itself is more acidulated at that point, or it might just be that pH is also inhibiting to malolactic bacteria. That mechanism is not clear at this point. We can say that in the literature, at least, it does seem to kind of have this effect for as long as they've run the tests. They don't know, like, does this last forever? Does it prevent malolactic, for example, in the bottle during sparkling, for like the second fermentation of sparkling? But people are talking about using it for that because it does seem to have a persistent effect for as long as they've run the tests so far. And most importantly for us in this particular experimentation, because it has been approved for use in the United States since the mid-1960s, there are already commercial products on the market for this. So Lafort and Vasson both have these products, and probably other companies do as well, but these were ones that were easy to get. So Matthieu ended up using the Lafort product, which is it's like fumaric, and then CTRL is sort of a subscript at the top. So that is fumaric acid. Then the other one we wanted to play with a little bit was Hideki tannin. This is an Enartis product. And unlike the other ones that we've talked about that are just dealing with that antimicrobial portion of being low sulfur, Hideki tannin is marketed as being both antimicrobial and antioxidant. And so that sort of was attractive as an idea, at least in this particular experimentation. So the philosophical underpinning of this particular product is just that, tannins in general do have these antimicrobial and antioxidant functions to them because of how they work in plants. They're kind of defense systems for the plant. When the plant gets invaded by fungal pathogens and that sort of thing, tannins are there really to defend against that. And the primary way they do that is by binding up proteins in these invading organisms. So they've got that kind of antimicrobial property to them. But they're also antioxidant in the sense that when these invaders come in, they do tend to sort of set off a free radical cascade in the cells of the plants. And so the tannins themselves also kind of help to quench that oxidative cascade. They do that by chelating metals, and they also do that by kind of scavenging oxygen themselves. So all of those properties sound like if we could find a good application, or we could find a good version of that, it might be useful to use in this application. So there is kind of, this isn't just something Vineyards is telling us. There is some evidence in the literature that phenolic compounds do have these kinds of properties. So there's a series of papers of looking at individual little phenolic compounds and testing them against different microbes. And in some circumstances, they show the effects that you can see here. So the first picture, the one on the top here, is just a scanning electron micrograph of intact cells. You see there's lots of cytoplasm. They're filling their cells fully. They're nicely formed. Everybody looks healthy. The second picture here shows what happens when you treat Enococcus. These are Enococcus cells. When you treat those with a particular tannin, some of them still look good, but some of them look a little bit ghosty. And we even have a couple of examples of ones there that have kind of burst apart. So given the right tannin at the right dose, you can start to see these cells kind of being inhibited in this very clear way. So the Hideki tannin itself is basically a mixture of tannins that have been shown to have this kind of antimicrobial property. And like I said, it also in the product literature says that it has an antioxidant property. So we wanted to include that in our test. So with all of those different things, Matthieu set up his experiment. It was a little bit complicated. So Matthieu, do you want to tell us a little bit about how you set things up to kind of test all these different iterations of things?
Yeah, so we pressed we pressed the grapes, all cluster, sparkling wine. So all cluster, 2/3 of the press, the 2/3 of the press go for my for what I keep for the sparkling, and the last third is being used for different wine, because I wanted to do one batch with 20 ppm and one batch with 50 ppm, and because I wanted to have a homogenic batch, I've filled up my press. I filled up one tank with everything with 20 ppm, and then after, as soon as everything was filled up, then I rack off a part of the juice where I added another 30 ppm to give me a total of 50 ppm. So I had one tank that had 20 ppm and the other tank that had 50 ppm. So that was giving me my two different batch from the same juice.
So that was a very nice way of making sure that we kind of started with all the same stuff. So from there, as Matthieu said, we have sort of 3 different treatments that came from that 20 ppm batch. So there was just the control that just got the 20 ppm. There was one treatment that went all the way through fermentation and then was treated with the Hideki tannin at the end. And then there was another batch that went all the way through fermentation and then was treated with fumaric acid after that was complete. That other tank then was used, we had a third treatment, so a fourth component here. We have control plus treatment 1, 2. Treatment number 3 was just that sort of higher sulfur at crush. And then we had a fourth one that was that higher sulfur at crush plus the Hideki tannin. So in total, we kind of have 5 different iterations here, a control plus 4 treatments. For each of our treatments, we had 2 barrels each. For the control, we had 3 barrels each. So another way to look at that would just be this table. This is kind of how we put it in the report. And I guess I would also say in terms of the amount that we used, and in this case, Matthieu really wanted to know if it makes a difference, and if so, what difference does it make? So he chose kind of the higher treatment level of both Hideki and fumaric acid. So Hideki, the recommended treatment level, somewhere between 5 and 10 grams per hectoliter. He went all the way to 10 to make sure that he could see the effect if it was there. The same thing with the fumaric acid in the literature, somewhere between 30 and 60 grams per hectoliter seems to be the effective dose. Okay, so all of this went all the way through, and then we basically just, everything else was the same. So in terms of all of the other cellar operations were the same, we let these go through, and then we just started checking them. So we did we did check them right after they finished fermentation, just to make sure that we were sort of starting with comparable things. These were all barrel fermentations. Things can go differently in barrel fermentation, so we wanted to make sure that things had gone smoothly and the same. So this is kind of the view of all of the chemistry that we got from that first thing. So there's a couple of things I wanted to highlight here. The first is that we can see in the total sulfur column, I've highlighted the last two in green. Those are the ones that got higher sulfur at crush. We can see that that did indeed increase the total sulfur. We can see all of the total sulfurs are above 50. So by the textbook, these should be inhibitory rates themselves. But in this case, we do have a higher rate in our higher rate. So our higher rate gave us a higher rate, but that's good to know. We can also see that even though Matthieu did treat them with sulfur, with SO2 after the completion of fermentation, that's all been bound up already. So already by the beginning of October or November here, he's really aging these with no measurable free sulfur in those wines. And then the last thing we do need to notice is that barrel 403 has already started has some malolactic fermentation that's already occurred. Because we did get the Hideki in there after fermentation, most likely this is something that happened during fermentation and is not an indicator that Hideki itself is not inhibiting, at least at this time point. This also kind of gave us a view of what happens if you kind of treat it after it's already started. So we can keep an eye on that to see, does it continue to progress, or do we essentially stop that progression by treating it with Hideki along the way? I will say that we took this exact same chemistry multiple times. So we took chemistry on all of the barrels in November, December, February, and April. We did that because we wanted to see if the malolactic does start to happen, when does it start to happen, and does it happen in all the barrels or just a couple of the barrels? I will also say there's some information that's not shown here that we did get every time, that these did go entirely through fermentation. There's no residual sugar, but more importantly, color intensity is part of what we measure with this particular analysis. And for all of the wines at all of the sampling events, the color intensity was non-detectable. And I say that because color intensity can sometimes be a marker for oxidation, because as it gets browner, the color intensity will actually go up. But in this particular wine, we really don't have a lot of phenolics that would be expected to brown because it is a gentle press for that sparkling wine cycle. All right, so when we look at what happens to the malic acid, we get this graph. Now I realize there's lots of different things on the graph here, so I did color code them so that we could look at them a little bit more holistically. So all of the control barrels are coded in they're colored one of the shades of blue. So we have 3 different control barrels. Those are all in blue. So if we look at those, they all kind of started with all of their malic acid intact. But very quickly, we have one barrel, it's barrel 211, looks like it kind of starts to drift a little bit between November and December. That malolactic fermentation speeds up a little bit by the time we get to February, and between February and April, it completes malolactic fermentation. So that control was not enough to keep it. When we look at our other control barrels, we have that brighter blue. Seems like that one kicked off malolactic fermentation a little bit later, but it does look like somewhere between, what is that, December and February, we do see that it's starting to move a little bit, and we see more pronounced movement by the time we get to April. And then our third control barrel is kind of that grayish color, and you can see that one took even longer, but by the time we got to April, that one was also starting to undergo malolactic. So we do actually, in this case, have some good controls that we know if we didn't do anything, they would go through malo. So the next set that we'll look at, actually, I would like to look at the, let's look at the fumaric acid ones, because those are kind of the next cleanest, easiest ones to look at. We only had 2 of those barrels. Those are ones that are shown in red or orange, and they're really kind of clumping very closely up, along the way, and they're not really moving at all. So fumaric acid in this case, at least in these 2 barrels, was sufficient to prevent malolactic fermentation. We actually have 4 Hideki barrels, and we have 4 high sulfur barrels, but 2 of those are the same one. So let's look at Hideki first. The Hideki only barrels are the ones that are shown in green. And we can see that, that darker green one is the one that started with a little malo that had already happened. That's the one that we saw in the last slide. But we can see by adding Hideki, or by chance, we can't tell for sure at this point, that didn't seem to progress anymore. So even though we had a little bit of malolactic that probably happened during fermentation, that didn't seem to progress any further. The other Hideki only barrel is a lighter green, and it's basically just clumping up with the fumaric acid ones. It didn't go off at all. So that makes us think Hideki's doing a pretty good job. Unfortunately, if we look at our Hideki plus high sulfur barrels, we see that one of those did go not only a little bit through malo, but all the way. So that's that dark purple line that, given in about, it seems to hold steady until it gets to February, but then once you get to February, it actually goes through malolactic fairly quickly. That's one that has both high sulfur and it has Hideki in it. So our barrels that just had the high sulfur, those didn't go. So if we sort of look at that, if we take a step back and sort of look at it, we had 3 of 3 control barrels did go through at least some malolactic fermentation. Of our 4 Hideki barrels, we had 1 of those 4 did go through malolactic fermentation. Of our 4 high sulfur barrels, 1 of those 4 went through. Fumaric acid, we only had 2 barrels, but neither of them tended to go through. So we did also look at lactic acid for these, really just to say, when we see malic acid going down, do we see commensurate lactic acid going up? Basically, this is kind of the mirror image of what we just looked at. And this data basically tells us exactly the same thing. As we see the malics going down, we do see the lactics going up. So when we looked at all of this data, Matthieu and I were thinking, this could just easily be a data only kind of project. We maybe don't need to look at, anything different in the sensory. But I did go to King Family so that we could taste them together and kind of just confirm that decision. Matthieu, do you want to tell them what happened when I came to taste those wines with you?
Yeah, I can say that. I think the general feeling, it's the wine were tasting fairly tired. Because on the purpose of experiment, even if I knew my free sulfur post fermentation, my first free sulfur were already at 7 ppm or less than 7 ppm. So I could have added sulfur, but I did not do it on purpose. And so all the wine I feel did taste a bit tired already. I feel like they were borderline oxidized. And even if the color didn't show any oxidation, because again, like with a gentle press, there's not a lot of oxidized phenolic, but I did feel the wine was lacking a bit of freshness, I would say. And when we were tasting all of them, the Hideki addition was the only one that was showing some brightness into it. So they were into the aromatic profiles. There were fairly significant difference between the Hideki and the other wines.
Right. So at that point, we thought it might be worth it to see if that difference was translated as we kind of looked at it at a triangle test. And I will say, when Matthieu and I tasted these, it was a big difference in terms of what they tasted like. So we decided to go ahead and do some sensory on this, really just comparing the Hideki with the control. So those other ones all everything else kind of tasted the same as the control, but that Hideki seemed to have a different sensory profile to it. So I've put the key up there so that you can know which one was which. And as you're looking, I think Jenna's going to go ahead and launch a poll for us. We'd like to know if you were able to tell the difference between these wines or not. So if you could, once you figure out which which one was which for your group number, go ahead and tell us, were you able to tell the difference between the wines?
Joy, are you able to share the poll? It's not giving me access.
Let's see. I may need to, I can't really see it right now, so I'm gonna have to stop sharing briefly. And then maybe can you do it now?
Let's see.
And maybe that you can't share at the same time.
No.
I haven't done this sort of whole thing in a while, so.
I know. I've created something different though. We're going to pivot a little bit. We'll see how this works. So I've just shared a link. Chat.
I actually can do it. I can launch the poll. So let's go ahead and do that. It looks like for whatever reason, it gave me the ability to do that.
Okay.
So I'll take it. So yeah, if you guys can tell us if you could tell the difference between the wines.
I'm not seeing the poll. Are other people seeing the poll?
Yeah, I can see the poll. I don't know if others can or not. I think Jenna, because you and I are on the same
account.
On this account. Yeah. So
I can see it.
Okay. Thank you, Jeremy.
Can you share the screen with the result, with the experiment, with the numbers? Again?
I'm not sure if I can share at the same time. So let's see if it, let me go ahead and I'll go ahead and end the poll right now. And looks like about 65% of people could tell the difference between the wines. So we'll look at that together in just a moment. And Matthieu, I'll go ahead and it looks like I have now completely messed this up. Let's see.
You're welcome.
We work out all of our technical difficulties and then they just rear their ugly head. Okay, let's see. Here we go. I will share again. Share that and then play. Okay, can you see them now, Matthieu?
Yeah.
Okay. All right, so for those of you, so it does look like we have quite a few people that were able to tell the difference between the wines. For those of you that were, can you share something about what was different between the wines for you? Let's see. And I have to get to a point where I can see the chat again. So you can either write that into the chat or you can unmute yourself and just tell us what was different. So for those of you, there are quite a few of you that could tell the difference. What was different for you between the wines? Don't be shy. There were lots of you. And again, you can just write it into the chat if that's an easier thing, or you can unmute yourself.
It really took me a while to get there, but I did notice more acidity and freshness in the control, in the aromatics and on the palate. Okay.
Which group were you?
Group 1.
Okay. It's funny because I've got the, I had the tasting them blind, knew it was my wine, obviously. I knew what I was looking for. I was looking for freshness, and I was able to find the control. I was good for, I was able to find the control. And for me, the control was different than the two other wines. But I thought the control was the ID key. I thought I had more freshness in the control, same thing. What I was, so I don't know why, but like this time I had exactly the opposite feeling of when we were tasting it last time.
Okay, yeah.
I had the same opinion. I thought they were hugely different. The Hideki was very bruised and lost all freshness, and the control was correct.
And that's interesting because that's essentially exactly opposite from what Matthieu and I were sensing when we were tasting them before. I will say that, I think so much of this is it's because they're already at this place where they've been at low sulfur, maybe not topped as much as we wanted them to be in barrels. They're kind of already right at that turning point of oxidation. And so I wonder, we do a lot to make them move too, or we do a lot to kind of mess with them when we're preparing them, right? So they're coming out of the barrels, they're going from, you know, when we pour them from the big bottle into the little bottles, that kind of thing. And so I wonder if that was also, you know, changing what or causing differences in what we perceived there. So I will say that the ones, when you have ones that are cloudy, and we have a couple of things on that, I will say, I know it's hard to not pay attention to that. But when we have these lees aged white wines, sometimes they do come in cloudy, and honestly, you might be getting poured from a different part of the bottle, that your two controls might be poured from a different part of the bottle. And so you might have more cloudiness in this one and less cloudiness in that one. So this is where if we were doing this in person, we would give them to you in black glasses, but unfortunately we can't really do that there. So I know it's hard to not pay attention to whether they're cloudy or not, but really that cloudiness doesn't always mean what we think that they come from the same bottle necessarily. So
yeah, my IDK tasting, like one was blurry and the other one wasn't. And
yeah,
so that,
yeah, exactly. So
that looks through a challenge, because you keep wanting to find a difference between these two, and there were not. So.
Right, and that's very hard to do, especially again with this particular with a virtual session, because we don't want to, you know, filter the wine, because that's just going to give us way more oxidation along the way too. So I do see lots of things in the chat here in terms of kind of aldehydics and aromatics and that sort of thing. The one thing that we were really concerned about when we started to think about adding Hideki to sparkling wine base, we're adding a tannin. And Matthieu was adding this tannin at kind of a high level. And the one thing that I haven't heard anybody say anything about, and I don't see in any of your comments, was anything about astringency. Right. I didn't even ask about astringency because I didn't want to like bias your answer to it. But one of the questions with, you know, can I add this to my white wine? You know, you can go back and taste those now to see if you perceive any difference in astringency. But in this case, I do feel like we've kind of gotten it where this particular tannin does not seem to be presenting a lot of astringency. I would be curious if anybody did see a fair amount of astringency along the way. Because I'm sharing my screen, I can't see.
It didn't bother me. Like for me, the astringency of the tannin didn't bother me. Yeah.
So, okay. So with that, I would say, does anyone have any additional questions about this particular experiment? We do need to kind of move on to the other ones that we've got queued up here. We will make sure that we process your sensory data pretty quickly and kind of send those back out to you so that we can see what that looked like when we were tasting everything blind and how that lines up with the chemistry that we saw along the way. So any other last minute things? All right. Okay, so let's go ahead and move on to our next set of experiments. And that's going to be looking at sulfiting agents. So again, there's lots of different ways that we can sort of put sulfites into the wine. And so we wanted to look a little bit at that today. So we were originally going to do a little bit of a poll, but in the interest of time, I'm going to kind of go through this relatively quickly because I think most of the background here is pretty commonly known for most of us. So, you know, when we think about ways to add sulfur to the wine, there's lots of different ways we can do that, right? Probably the most common way is to use KMBS. KMBS is very inexpensive. It's got some moderate safety considerations. You don't want to kind of breathe in I'm sorry, I just saw that Kirsty had a question. I just saw the chat because I can't see the chat while I'm showing my screen too well. So Kirsty wanted to ask, did the fumaric acid change flavors? I think that is a good question. Did anybody notice any differences in the flavors with the fumaric acid? Sorry, I didn't see that. Kirsty,
I didn't taste any difference in the fumaric, and that's the reason why we didn't decide to not even show it to the tasting, because both of us with choice, there were no. I mean, yeah, it was. I didn't taste any difference.
Okay.
Yeah, and I would say in this case we also didn't see any change in the pH like we see sometimes in the literature. So in that case, it seemed to not be kind of changing that portion of things. So I'm sorry, Kirsty. I'm sorry I didn't mean to.
No, that's okay. And
go over that
also,
one.
I was just curious because the fumaric acid was the one that appeared to have the most impact in terms of preventing malolactic from going through. Curious if Matthieu, if you use the fumaric acid again.
I don't know yet. I don't have any problem using it because it did work well. I'd like to keep experimenting with it and be just to confirm that it doesn't really impact anything to the wine. What could be interesting, but I don't have enough volume to do that, but would be to see if there's a difference with the second fermentation, because we're going to do a second fermentation, and if the fumaric is going to interact with it's going to create malic during the second fermentation. I'm not sure if that's something that we want, but anyway, it works well. It's easy to use. I'm not opposed to keep using it. I will keep doing more barrels with the IDK this year. I don't like the result of what I'm testing right now, but when we were testing it straight out of the barrels, I did prefer the wine with the IDKs and the one without the IDK. So I'm not going to suddenly switch everything with the IDK, but I'm going to keep playing with it.
Thank you.
And I would say, just in terms of the sparkling, there are a couple of kind of folks that do research on sparkling wine that are starting to look at what happens to the fumaric acid when you use it in there. So we'll keep an eye on that research and see what comes out of it. So. Okay, so moving on to our sulfiting.
It looks like we also, sorry, it looks like we have a hand raised. Michael Honey.
Oh, gotcha. Sorry, and I'm going to stop sharing my screen for just a second here, because I think that's what's getting in the way here. So Michael Honey, did you have something you wanted to say?
Yeah, Matthieu, I was curious on when you go to bottle with this wine. Yeah, when's your target bottling? Because it looks like you're not much was happening with ML through the beginning of February, and then a few barrels started to go off. So I was just curious on your timetable with the wine and taking it out.
Right now, it's being filtered, and on Monday it's going to be bottled. So my timetable is fairly short. I think I was able to keep my on the rest of the batch. I was able to keep my sulfur a little bit higher. So I don't think I still think I'm going to have a little bit of malolactic fermentation going, but I don't think it's going to be a huge. I still think I'm going to have more malics than lactic into my wine. Let's say it this way.
Yeah, and I think that we saw the malics start to move quite a lot. When things started to warm up in the cellar. These are aged in the barrel. And, once we got to February and we started getting those warmer days, that's when we really saw those things kind of moving more. So that would be one of those considerations. So, okay. So anything else before we move on? I can actually see you all now, so I can see if anybody's got things to say. Okay. Well, our next experiment was done by Kirsty Harmon. And I was just gonna, give a brief overview. We're going to kind of move into different sulfiting agents, but maybe we'll talk about any background we need to as we're going. So Kirsty, our flight 2 was an experiment that you did. So do you want to tell us just a little bit about what your experiment was and why you wanted to work with that question?
Sure. So I think a question that I always have is the best way to add sulfites to barrels. As most of you might know, I'm a fairly big believer in SO2, and I'm not shy to use a fair amount of it. But the delivery of how it gets into barrels, whether that's KMBS or Effergran, was a big question for me. I was reluctant to use Effergran for the longest time because I found it is expensive. But I started using Effergran a few years ago because of the convenience of not having to stir the barrels after the addition. And just the ease of use. So I started to use that a few years ago, but really wanted to challenge myself to make sure that it is doing what I think it's doing. It's effective, and it's worth the extra money. So I had Rousson that was fermented. The initial addition was done with Effergran. Then it was put into 2 different barrels, and then from then on out, it was either an Effergran addition or a KMBS addition during aging.
Great. So if you guys are not familiar here, we'll go ahead and give you a little picture of what happened there. So yeah, if you're not familiar with the Effergran, these are just this sort of effervescent blend of KMBS and potassium bicarbonate that when it sort of hits liquid, it literally kind of starts to fizz. So Ephragran is the Enartis version of that. Enodose is the Scott Labs part of that. I'm sure other companies also have other proprietary names, but they kind of work in a similar way. And as Kirsty said, KMBS is a lot cheaper. It comes out to be about 2 cents per gram of SO2 added, whereas Ephragran comes out to be something like about 25 cents per gram of SO2 added when you kind of do the math of what's currently out on the market. So in this case, Flight 2 is basically, as she said, this is a Roussanne wine. So Kirsty, you're normally adding KMBS at crush, but you're using Ephragran at the end of fermentation. Do you want to talk a little bit about kind of why you're doing that?
Because I feel like at crush, you're getting good movement and kind of mixing of the KMBS into solution. And I don't feel the need to add Ephragran at that point. But in barrels, I'm really trying to avoid having to stir barrels or stir tanks once the wine is sort of settled and aging. So that's why I choose to use them at different times.
And you use the granulars and not the tabs. Do you want to tell us why that is?
I've used the tablets before and found them at the bottom of the barrel when racking the barrel. So I think they're supposed to dissolve completely. Maybe they're not supposed to dissolve completely, but it was kind of disconcerting when I racked the barrel and saw the tablets on the bottom.
They are supposed to dissolve completely, and I had this issue too in the past. If the package is damaged, then they will not dissolve properly. So
I've had the same thing happen with Ephragran as well. It's just a little bit more obvious with Ephragran because it clumps up. Yeah. Or at least in my experience, it clumps up, so you know something's off.
So the product information for all of these does say that it's hygroscopic, meaning it'll kind of take up the moisture in the air around it, and that does make it lose potency. It turns out so is KMBS. So if you have that bag of KMBS that's been sitting around for 2 years in the back of the winery, it probably has also lost some potency along the way. And if you use liquid sulfur, if you sort of bubble gas into the liquid, you know that it loses potency over time. The one good thing about that is that we can actually measure that, whereas with these other products, we can't necessarily do that. So I would say if no matter which KMBS or which effervescent product you're using, they really do say that once you open the package, you want to use it relatively soon, which is why they come in these little kind of individually packaged little smaller packages so that you can add little bits at a time. Okay, so you guys know what you have in front of you. Again, everything was kind of made along Kirsty's normal winemaking ahead of time. They went down into barrels, and then any subsequent additions were done either just with Ephragran or with the KMBS. So we will take just a moment to look at the fermentation curve itself, mostly with the idea of thinking about when our sulfur is binding and when our sulfur is not binding. So the fermentation here was really good. It was, the kinetics were very smooth. There were no problems along the way. There's nothing in this particular fermentation that makes us think that we're going to have an abnormal amount of sulfur binding along the way. Sometimes if the yeast kind of labor toward the end, if you have residual sugar, then you can anticipate that you'll probably have a little bit more sulfur binding. In this case, Kirsty did look at the SO2 levels every 6 weeks or so. And so the graphs that you have in front of you, or that I'm showing now, the top graph is showing what the actual SO2, the free sulfur was at that time period. The bottom graph is showing how much free sulfur has bound since the last time period. So in the beginning of, or the middle of January, these wines were somewhere between 17 and 21 parts per million of free sulfur. But if we look at that, at the bottom graph, these got like a 60-part addition at the end of fermentation. So we can see that between that end of fermentation and the beginning of January, we had about 40-ish parts per million bind up. So then when we kind of go to the next month there, and when she checked the next time in March, much of the free sulfur had bound up by that point. So she was somewhere between 4 and 6, it looks like. So when we look at how much had bound there, it was basically whatever that difference was between what the free sulfur was in January and what the free sulfur was in March. The first thing I noticed about this is that there's not huge differences between the two modalities, right? So it doesn't really look like there's big differences between whether she's using Effergran or KMBS in terms of what the free sulfur is or how much is binding. I think the more interesting thing is really what's happening, for example, in March, where there's not a lot of free sulfur in there. She does a 25-part ad, and then she gets, 5 days out, or, she waits her 6 days to see if that binds, and most of that turns out to have bound along the way. So I would say that, just looking at the numbers here reminds me that if I let my free sulfur numbers go down, I build up enough acetaldehyde, there's a lot of binder along the way. And so sometimes we're not really aging at the target that we think. So Kirsty, in this case, your target was at about 25 milligrams per liter. We see and that's probably a little bit of a shift from what you would normally be aging at, and you're still kind of not there. So do you want to say just a couple words about that?
Yeah, I think it stresses the importance of rechecking SO2 a few days after the addition, especially when the SO2, the free SO2 has gotten fairly low. Just because I think that initial ad, you feel like you're going to be fine, and you're really not until you double check it. So I think that was a good lesson for me to check more frequently. Obviously, between the 13th of January and the 1st of March, something was happening. Whether that's, loose bungs, not topping properly, I'm not sure, but
we have lost Kirsty. It looks like her internet has gone out. I'm going to go ahead and hopefully she'll be able to kind of come back on. And Jenna, are you back? Excellent.
Yeah, I'm back. I'm not sure what happened, but I hope. So I think I need to check more regularly, and then just check again after an addition if it's important to be at the target that you're looking for.
And I would say that, for those of you that kind of do one big ad at the end of fermentation, put the bungs in and ignore it. Just kind of be aware that you might have a lot of sulfur binding up there. So just understand that that's probably what's happening in there to some degree. So again, here, and just in terms of that comparison between sulfiting agents, doesn't look like there's huge differences in terms of binding versus free sulfur there. We did want to look a little bit at the difference in potassium, because KMBS obviously brings potassium with it. The Effergran is basically a 75% KMBS plus potassium bicarbonate. So you actually get even more potassium per sulfur, per amount of sulfur. And so we did kind of look at what the potassium looked like here. And once again, with potassium numbers, there's a lot of things going on to affect potassium. But we can see that, it looks like Effergran has about the same amount of potassium and KMBS has less. So it's hard to kind of interpret what's going on there, but most likely we've got, and this is the same lab and the same technology that's doing that. So, most likely we've probably seen some precipitation of potassium bitartrate in our KMBS. In our Effergran, if we hypothesize we've seen that same amount of precipitation, then we are seeing a little bit more potassium kind of building up along the way. But again, that's kind of a hard thing to know the difference between. We didn't see any differences in the pH along the way, but we did, just because we saw this, we did send these for cold stability testing to see if we do see any differences in cold stability, because we have more of that potassium in there. So those numbers are ongoing. But then there's one other thing that happened with Kirsty's experiment that we did want to bring up a little bit, and that has to do with the sampling technique for sulfurs itself. And this is a little bit of this is a little bit off topic, but I think it's really important as we think about managing sulfur dioxide. So as we get ready for any of these sensory sessions, we take one last set of wine samples, just to make sure that the SO2s are relatively the same and nothing weird has gone on in the wine since the last time we sampled it. So we did that with this experiment. On April the 14th, we sent this to the lab in France where we send things, and we got these free sulfur numbers. So I sent those to Kirsty, and I was like, so just so you know, it looks like the Effergran's holding better. And she said to me, oh dear, this is what I got in-house. So Kirsty, do you want to tell us a little bit about about kind of how what we eventually thought that was probably going on there?
Sure. So a couple of months ago, I bought a Sentia analyzer, and one of the things you can measure is free SO2. And on the brochure, it shows the gentleman in the barrel room taking a sample, directly from the barrel onto the Sentia with a little pipetter. So I thought, well, if it's on the brochure, certainly this is the way to do things. So I went in, took a sample out of the very top of the barrel with a little pipetter. Mind you, it's 50 microliters, so a teeny tiny amount, and took the sample, and that's this 417 results, which sort of concerned me. So took another sample using an actual thief to take the sample, and those are the results that we saw. So that reminded me that it's important to check SO2 often, but also how you're sampling makes a huge difference, because had I just gone with the 417 results, I would have added sulfur. So, I would have added sulfites to the Effergran barrel when actually I didn't need to add to either one. So I think it's a good reminder on a lot of levels, but it's a great reminder in that how you're taking the sample does really impact your results.
And I think it's one of those things that, like, you get so used to whatever your protocol is, and then when you change to something new, you don't realize all the things that were sort of baked into your last protocol to make sure that you're getting a good sample. So I think, thank you, Kirsty, for helping us to see the actual numbers behind that, because I think they're pretty powerful to look at. And I would just say, in terms of kind of taking your sample for SO2, if you take your thief and you put your thumb on the top of the thief and put the thief all the way down in the barrel and then let the wine come in, you're essentially sampling a little bit more of the depth of the barrel. But it's also something to realize that, the wine that's at that boundary layer at the top, it does see a lot more oxygen, and it does sort of deplete a lot more sulfur. So a lot of our oxidation might be happening there. So the more untopped your barrels are, the bigger that surface area is, you really are going to have more wine that are in that's in sort of that lower sulfur context as well. And then one other thing there, if you are sort of sampling, the principle applies if you're sampling from tanks, thinking about how much, if you've got if you kind of are going from a valve, realizing that, there's probably some air leaking around that valve a little bit, or there could be. So if you're sampling from a valve, you do want to dispense a little bit of wine through that valve, discard that wine, and then take a new sample so that that you're sampling wine that comes from within the tank itself, just to get a little bit better, more accurate number of what that sulfur is along the way. So, okay, so with that, let's go ahead, and this is not advancing. There we go. Let's go ahead and talk about sensory impression. So I'll give you your key one more time, so that you can know, and then I will stop sharing so that I can actually see what's happening here. So, so I would love to see once again if we were able to tell the difference between the wines. So I think that's, there we go. So were you able to tell the difference between the wines in flight 2? Yep, I see people coming in there. So again, we were interested here in kind of the ability, the efficiency of this, but we were also interested to see if there were any sensory effects that that kind of came up as we were using these different sulfiting agents.
Maybe I missed the result, but I missed the flight numbers and what was what.
Okay, hang on just a minute. What group are you in, Matthieu?
I am group 4.
You're in group 4. Wine 909
yes.
is the one that's different.
Okay.
And that one is KMBS.
Okay.
Okay. If you're in group 1, it's wine 658 is different, and that one is Effergran. If you're in group 2, it's wine 598 that's different, and that's KMBS. If you're in group 3, it's wine 777 that's different, and that's Effergran.
Right. Me too.
Okay, so it looks like, let me go ahead and end our, no, we just picked one more up. Any more voting? Okay. So I'll go ahead and share those. Hopefully you guys can see them. It looks like we have about 61% of folks were able to tell the difference between the wines. And again, Jenna will run our sensory statistics on that, but that will be a significant result. And Wendy, I'm sorry you're not seeing the poll. It may be, sometimes it depends on your version of Zoom, unfortunately. So maybe you and I can talk. Yeah, maybe it might be your right. So, okay. So, the next question is what's different between the wines, because people are already starting to type that into the chat. So thank you for those of you that have done that. So if you want to put whatever you thought was different between the wines in the chat there, Michael Henney says that the KMBS seemed more aromatic. The Effergran was a bit less heavy on the palate. So maybe a little bit, more lifted on the palate. And I think this is one where we did ask about perception of acidity, which I think was Kirsty's and my impression that there might have been a difference there as well. And then AJ got some bitterness on the finish with the KMBS, and she didn't get that with the Effergran. AJ, that's interesting considering what we found with your experiment as well, which we'll talk about in just a minute. And then Rick says, let's see, we've got KMBS seemed more mouthfeel and aromatic. So the aromatic part of that would be consistent with what Michael Henney was saying. The mouth and the mouthfeel there. And then Shai is telling us group 2, KMBS showed SO2. So that was more apparent SO2 on the KMBS. And the Effergran had a minerality, which we might associate, I guess, with some of the extra minerals that we see in there. So, okay, other differences between them. I'm surprised that this many folks, that we had that many folks with differences between the wines. Okay, so Kirsty, given all of this, what do you think about your KMBS versus Effergran? Is it worth the extra cost and the not mixing? From sort of what you've seen so far?
I mean, from a purely logistics and operations standpoint, Effergran, I think, is the way to go. For me, I don't like to stir barrels because I also don't generally want to kick up a lot of the lees, even though Effergran does kick up some lees, not to the extent of stirring with a barrel stir, at least in my experience. I am surprised that this small amount of, like, basically it was 2 editions of either KMBS or Effergran, that in 2 editions worth of time that we see a difference. That's really surprising. And I might have to do this again with red wine as well, simply because if we're seeing differences in potassium, we're already struggling with potassium issues and pH issues. I don't know. It opens more questions than it solves, I think.
Well, and I would say, yeah, if we wanted to do that again, sort of from the original editions or with multiple barrels too, I think sometimes we can ask the question, like, there's enough there to spark our curiosity, but I'd be curious to see if we see those, if it's just the difference between 2 barrels or if it's the difference between what we're doing to the barrels in that case too. So, but we can definitely talk about some options there. So, okay, so let's go ahead and move on to our 3rd experiment. This was an experiment done by AJ at Hark. And AJ, you actually were the one that started us thinking about different types of SO2. So tell us a little bit about what your experiment was and why you were interested in that question.
So I experimented with liquid SO2, so SO2 gas barged into water, KMBS, and then instead of Effergran, I did enodose. What had happened was about a little over a year ago, I was at another Winemakers winery, and that winemaker had me taste and sample wine, and I got KMBS immediately on the nose. And I've used KMBS when I haven't had access to liquid SO2, and it got me thinking about, and I mean, it was just kind of an immediate, like, oh, and I know what this is. I know it's like, I knew it was KMBS versus the liquid SO2. And it just got me thinking as to the differences on the palate that we're experiencing with the different modes of sulfuring that we're using, whether it's I call them the Alka-Seltzer tablets. So the effervescence, or if we're using liquid, or if we're using KMBS. And then also the effects of, the potassium and that you get in KMBS and the enodose versus with liquid SO2. So that's.
So in this case, AJ was using the enodose tablets. So Kirsty was using the granulars, and AJ was using the enodose tablets. But again, in both cases, these kind of come in these single-use packs where you can either add in a barrel, it's either adding 9 parts or 22 parts, I think is what it turns out to be, in single doses. So that might become important later. Now this one, we actually had a little bit longer separation between the types. So in this case, this was a Petit Manseng fermentation. It all fermented together in an egg, but then it was subdivided into its treatment barrels before it got its first SO2 addition. So the first SO2 addition was 110 milligram per liter addition, but that happened with either KMBS or liquid SO2 or the enodose tablet. So in that case, everything post, that first fermentation addition was that different type. So much like with all of these experiments, when I went to go visit AJ on that kind of last visit, we were like, they might all taste the same, so we maybe won't do sensory on them. And then we tasted them, and we felt like 2 of them tasted more different than each other. And so those are the 2 that we chose to have you taste for this particular experiment. So in this case, this was we just had you taste the difference between the enodose tablets and the SO2 solution. From our tasting in the winery, the SO2 solution and the KMBS really were fairly similar. And so this allowed us to do the triangle test. We will look at all of the data for all 3 of them, but just in terms of the triangle, we wanted to sort of look at those 2, which are the ones that we felt at that moment were more different from each other. So just to get a quick view of what happened in the experiment itself, this was a Petit Manseng fermentation. And so those of you that work with Petit Manseng know that it comes in with high Brix and low pH. And in this case, the fermentation, this was actually 2 different harvests of Petit Manseng. The juice was held cold, and then the next harvest was added to that juice, which is why we have 2 sets of juice chemistry there. But they were all fermented together. So they were fermented together in that egg. Fermentation went along quite well until it got to just shy of about a specific gravity of 1, which on Petit Manseng is not dry. So in this case, AJ, do you want to talk just a minute about where you were hoping to go with this and where you ended up kind of stopping with it?
Yeah, we were hoping, I was hoping to target like 1.3% residual sugar. And we ended up at it was like around 3%. We had in the past, I've harvested 2 separate picks at 21 and 23 Brix, or targeting those. And this time it was 26 and 28 Brix. And the Yans were low, as you can see. And well, it was a poor yeast decision on my part. And I just I don't think I fed it enough. So we got
well, it turned out to be a really good example for this particular experiment, in the sense that it sort of has these components to it that we would think would do more binding. So if we're really looking to see how effective is our SO2, we're really saying how much is it binding versus how much is not binding. It doesn't matter how we put it in there in those terms. So in this particular experiment, we ended up having lots of things that might be binding up our SO2. So the residual sugar here, as AJ said, turned out to be about 3%. We know sugar is going to bind our SO2. The acetic acid is kind of, we tend to see this with Petit Mansengs, but the fact that it kind of, labored along there at the end might make us hypothesize that we'd also have a fair amount of acetaldehyde. The yeast are going to make acetaldehyde as they're stressed at the end. So in that case, we actually have lots of things that are going to bind our SO2. So it was actually really great for the experiment, AJ. It may be not quite what you were thinking of for this particular wine, but we got there. So in this, Go ahead.
It was all for the experiment.
It was
totally.
all for the, yeah, all for science. So in this case, when we looked, again, once that initial dosage had been done, we went ahead and took full chemistry on everything. We're going to focus on what's happening with the sulfurs here. The first thing that jumps out obviously here is that, you know, our KBS and our SO2 solution of that 110 milligram per liter addition, most of that has bound, and we only have like maybe 10% of that left over. Whereas with the dose, we have a much higher proportion of that. As soon as I saw these, I did talk to AJ, and I was like, can you think of anything that might have happened in the cellar that would affect that? And AJ, I'm curious what you would say to that.
I wonder if the barrels were topped before the SO2 addition was done. So if some of that SO2 flowed out of the top when the bungs were put in initially.
So if you've used the dose tablets, they go all the way to the bottom. And
Yep.
so your SO2 is sort of coming out of the bottom as opposed to coming out at the top. So this may be a cellar thing. This might be something else. And that's where, again, if we might want to try this with multiple barrels to see, do we see this all the time? Or is this sort of one of those very curious things to look at?
This was not an addition I did myself. I was in the middle of doing 10 other different things, and I had one of my cellar guys do it. And so I wonder if that might have been the, if we overflowed barrels with that, and that's why we were seeing the low SO2s. And if it was,
I would say, yeah.
Did you,
Go ahead.
Did you add 110 grams of KMBS or 210, 220?
It was 110 ppm.
Of sulfur,
Yeah.
or of
Yeah.
KMBS?
KMBS.
Yeah.
Okay, so that's the thing, and those you follow what was on the tablet.
Yeah, so the addition was 110 ppm. I have to look up on my software and see what the gram percentage of that.
Okay.
Yeah.
I actually, so as soon as this came back, I actually went back and rechecked all the math on it. Matthieu, I was asking the same question. I was like, if it were me, the most likely thing I would do would be, be looking at the wrong thing in the conversion. So I went back. AJ's math was perfect on this, in terms of how many grams of KMBS needed to be added to get to the 100 milligrams per, or 110 milligrams per liter. But I think that is one thing to think about in terms of these different modalities, is that there's different sources of error for each type. So when you have kind of that single use pack, every time I'm adding, as long as I add this whole pack, I'm adding 22, parts per million. Whereas when you're kind of having to calculate it every time, there is a potential source of error there. But like I said, I did recalculate this one just to check, and everything was calculated correctly. So when we look at
for the sulfur solution, is it a sulfur solution that is pre-made? Is it the LAF4 sulfur solution that is pre-made, or it's in-house?
We sparge it here. We sparge it here, and anytime we do a sulfur addition using because that's what we primarily use is the solution. So every time we use it, we recheck to see what, with a hydrometer to see what the percentage is.
Okay.
Yeah, so those of you that aren't familiar with that, that's an excellent question. Also, just if you're doing that in-house, again, your SO2 solution does lose efficacy over time, but you can recheck it. Whereas again, these other, like your KMBS, if your packet has been sitting around for a long time, there's not really a great way of rechecking that. So pros and cons to both of those, I guess. So, okay, so if we kind of look at efficacy, this is kind of set up the same way that Kirsty's graph was set up, in that the first set of columns here is what AJ measured as her SO2 at the end of November, and then underneath that shows how much had bound up from that initial 110 milligram per liter addition, and then sort of following from there. So because the dose tablets sort of had better efficacy to begin with, we do see that they are much closer to what the target SO2 was than the other modalities. It does, tend to lose efficacy, or we do lose SO2 over time. But again, just because that original addition was much closer to the target, she tends to age closer to the target. I think it's really kind of the bottom one that tells us a little bit more about kind of what she's getting back in terms of what's binding and what's not binding. And what we can see is sort of those first 3 additions, it looks like she's got less binding in her enodose tablets than in the other modalities. But then once the enodose kind of starts to go down, so she has less free sulfur, that one starts to kind of have a little bit more binding. So this probably has a lot more to do with the actual free sulfur in the solution, how much is bound, how many of those binding sites are left to bind something new, rather than the modality that's actually being used to add to it. So that's an additional variable, but I think it's something to think about as we manage our SO2 rates. Either way, by the time she got to toward the end there, she did end up quite at the target right toward the end without any binding at that very last addition. So at that point, maybe she can expect that if she keeps up those kind of regular additions, she won't have as much binding going forward. One thing I wanted to look at here was just how much addition had to be done total. Again, when she had that big dose up front, she didn't have to do additions nearly as often as she did when she had with the KMBS and the SO2 solution that didn't have as much efficacy in that first set of binding. And then once again, if we look at the potassium, once again, we do see that those tablets do have a higher potassium than the other ones that we're comparing to. And so again, we get back to that question of what happened, if we had a little overflow at the beginning, but there is a little bit more potassium, whether that's meaningful or not, in terms of the cold stability would be something that we would need to test to know. That it's not a huge difference there, but we are adding potassium along the way. There we don't see a big difference in the KMBS and the SO2 solution. There's a little bit of a difference there as well. But okay, so thinking back to that, we're going to go ahead and look at whether or not we could, if there was any sensory differences based on this. So unfortunately, to launch the poll, I do have to take away the key here. So do take a look at the key, make sure you know which is which for your own purposes, and I'll go ahead and launch the poll. So once again, we're just looking at whether or not you could tell the difference between these wines. And Wendy, if you can't see it, you can go ahead and just write it into the chat. If you're still not able to see the poll, we can add your response that way. Looks like we have just a couple more folks to vote here. And the next question I'm going to ask you is, if you could tell the difference, let me know what the difference was between the wines for you. So it looks like here our numbers, we have about 53% of respondents could tell the difference, and about 47% could not tell the difference. So that one's a little bit closer than the one before. Although I would say that in a triangle test on this number of people, a lot of times that might be enough to still be significantly different. So for those of you that were able to tell the difference, I'm curious what the differences were that you were able to see. So Wendy was not able to tell the difference. And Wendy, I would just say you're not wrong. It just means that the differences were small, and it's important for us to know that too. So thank you for sharing sharing that there. Okay, so Vitor said that the group 1 sample 161 tasted more fruit forward. I'm going to have to look back at my own key here to see which one is 161. So that was the enodose tablet. Looked like it was more fruit forward to Vitor. And then Rick says that the SO2 had very slight mouthfeel, a little bit less acidic than the enodose, but that was a very small difference to him. So other differences that you picked up between the wines.
interesting to me because I got it. I couldn't tell the difference between, but when we tasted through and did KMBS here, the difference between the KMBS and the Enodose versus the SO2, the KMBS to me is prevalent. Like I said, in Kirsty's experiment, I got that bitterness on the back, and I get bitterness on that barrel of KMBS that I have here also.
Yeah. So yeah, that's why I was interested when you said before that it tasted like bitterness, because that was your note before too. So it looks like whatever differences there are, that they are probably pretty subtle differences here. So, you know, I think that goes back then to some extent goes back to kind of those other considerations. So, you know, cost and safety concerns with using the different types and what kind of the setups might be. I'm actually going to launch one more poll for you guys because I'm interested which sulfiting agents you're using in your winery. So we've talked about KMBS and liquid SO2, whether you're bubbling that yourself or whether you're purchasing that. As Matthieu said, you can purchase that like from Lafort. If you are using some other form, please feel free to do that. And this is a check all that applies. So if you're, you know, sometimes using the tablets and sometimes using KMBS, you know, go ahead and click both of those. But you know, I think that there's lots of different reasons to use different ones, but it is interesting to look at what the different options are. So, I don't know if, can you guys see these as they go?
I can't see anything, but I think that might
That's because you're
yeah.
you're online. Yeah. Okay, so I'm going to go ahead and I will share that just so that we see it. It does look like a lot of folks are using KMBS, some are using the fizzies, and fewer are using the liquid sulfur. Does anybody want to have, is there something about what you really like about your favorite modality that we have not talked about yet? Or some reason you're not using one of them?
I can just talk about the liquid sulfur that I used to do the liquid sulfur with a solution where you gas it and you almost kill yourself every time you do it. And I've started using the solution from Lafort. It's a 10% solution. It's a mix of potassium metabisulfite and sulfur, but it's still like mainly sulfur. There's two advantages of it. It smells much less than the regular sulfur solution, and it's a 10% solution. So when you need to do an addition, it's very, very, very easy to make the math, and there's less margin of error about like the sulfur addition. So it's expensive for just sulfur in liquid form, but it's so much easier to use. And yeah, I mean, that's mainly what they use in Europe. In France, you find that almost everywhere, and it's not as common here, but it's what I prefer to use for the barrels. I do use the tabs because of the, like Kirsty was saying, because it's super easy to use.
Yeah. Other favorites, other ideas of anything else to say about sulfur modalities before we go? I would agree with you, Matthieu, just in the sort of the safety concerns that come along with using that SO2 bubbled liquid when you're trying to set that up to do the bubbling. You need to make sure it's outside and good ventilation, and even when we're getting it ready to do the addition, you know, you certainly don't want to be breathing that in or getting in your eyes. So it's good to hear that there's an alternative to that. Okay, so I think at that point we'll go ahead and we will get together all of your sensory, all of kind of the sensory statistics from what you guys did for your sensory sheets today. Thank you for filling those out and for sharing your insights with our experimenters today. We want to make sure to thank each of our experimenters, Matthieu and Kirsty and AJ, for doing these experiments and sharing those results with us. And of course, to thank the Virginia Wine Board for funding our project. So just one more reminder, we do have a sensory session coming up on May the 24th in person, and we'll send out details on that hopefully early next week, as soon as we get those details nailed down. So thanks so much for your attention today, and we hope to see you next time around.